A very good morning to all of you. So, in energy losses, in previous lecture we have seen the different losses and we have tabulated it in table number one, that is minor losses in pipeline. Due to sudden expansion, this derivation we have done in lecture number 39, and then based on that we have come to the some losses, losses into the pipeline due to the minor losses. These are sudden expansion V1 minus V2 whole square upon 2G, sudden contraction V square upon 2G 1 upon Cc minus 1 whole bracket square, entry to pi, the minor loss is 0.5 times of V square upon 2G, exit to pi, the losses are V square upon 2G, and if there are bends, fittings, etc., then K times V square upon 2G is the uh, minor loss, and if nozzle are voided, the loss will be V square upon 2G 1 upon Cv square minus 1. Okay, so these on the tabulated form we have seen different losses, and based on that, major loss already we know, and then based on the this value of K for bends and fittings, it is given K is equal to 0.9 for 90-degree elbow, K is equal to 5.6 for gate wall, all half open, K is equal to 0.2 for the gate wall fully open, K is equal to 10 for blow wall, K is equal to 1.5 is the foot wall, which we are providing in the water tank to automatic close the supply. K is equal to 0.4 for the 45-degree elbow, and K is equal to 0.9 for standard T we are using for pipe fittings, and K is equal to 1.2 for sharp 90-degree bend. So these are the different K values for the bends and fittings, uh, this losses, minor losses. So therefore, this table, we have to remember the situations to the minor losses due to the sudden expansion, sudden contraction, enter to pipe, exit to pipe, pipe fittings, and nozzle, etc. And if minor losses are less than 5% of the major loss, then it will be neglected. It will be neglected. So in previous class, we have also seen the this different types of losses, and total energy line, that is energy gradient line EGL, and hydraulic gradient line HDL. Okay, so we have seen this. The hydraulic gradient line is the line representing pressure energy along central line of a given pipe system, whereas energy gradient line is a line higher by V square upon 2G compared to the hydraulic gradient line, and represent the, the total energy of the flow. So Eg will represent the total energy of the flow, that is Z plus P upon gamma plus V square upon 2G, and hydraulic gradient line is Z plus P upon gamma only. Z is the dotted line, not shown here. Okay, so these are the this is dotted head not shown in the figure. Here means in the figure. Okay, then also we have given you the example to solve. Might be many of you are solved this example. If not solved, then I will explain here. You can solve. So first of all, when there is example is given to you, you will try to find out what is given and what you want. You need to be find out. Okay. तो here यहाँ पर हम लोग देखेंगे कि दो रिजर्वायर है, रिजर्वायर 1 and 2 having level difference between three surface of water equal to 5 meter are connected by pipe AB and BC of diameter 20 centimeter and 30 centimeter respectively. Length of pipe AB is 300 meter and length of the pipe BC is 200 meter. The flow through the pipeline is 50 liter per second. Find the loss due to expansion and friction factor F. Draw EG line. Okay. So this you have to find out the friction factor in this example, and also you have to draw the energy line. So this example is given, and then based on this example, you write down the given and we have drawn the figure. Okay, already we have drawn the figure, and we have pointed out also how many losses will be going through this pipe in series, because this pipe is continuous, and that's why you can say that this pipe is in series, not in parallel. So that also you will learn today what is the pipe in series and parallel, what is the difference between these two. So here you can say that this pipe 1 having a length 300 meter, diameter 20 centimeter. We are flowing the speed of velocity v1, and so you have to draw the energy line. This is the your line EGL. This one is the EGL, and EGL is reducing as your flow proceeds. So you can see the first entry loss to the pipe, this at the entrance. Okay, so there is some difference between the reservoir level and this, that is entry loss. As you proceed further, there is then loss due to friction HF1. Loss due to friction HF1 is the major loss in pipe 1. Then again we will come the sudden expansion of pipe is there at this point, at this juncture. So this is nothing but the loss due to sudden expansion. Then again your energy line will be dropped. So first we will draw the energy line, then we can able to solve the example. Then again when you come at the end, so flow through the pipe 2, that is the, you can see the friction loss, that is HF2 in the pipe line 2 having a length 200 meter. Okay, this is not mm, this is meter. Okay, 200 meter. Okay. And again, when the water comes to the reservoir 2 here at this place, again there is loss due to excess. Here is also from the line. And this, so this is nothing but your EGL, that is energy gradient line, EGL. You have to draw first, and then we will solve the example. So in this example, you can see that in this example you can see that example is given. What is given? You can write down here the length L1. Sorry, to select the, okay. So length L1 is given 300 meter, and then diameter D1 of the pipe L1 it is given, D1 is given 20 centimeter, or you can convert into the meter, 0.2 meter. L2 is given, sorry, length of pipe L2 it is given uh, where it is L2 is given 200 meter, and D2 is given, diameter of pipe 2 is given 30 centimeter. If you write in meter, that is 0.3 meter. So, okay, this is given, and the difference between the pressure head, or difference between the head of the reservoir R1 minus R2, the level difference is 5 meter due to due to due to various losses various losses. Now you can see here this 5 meter is equal to the different losses. What are the different losses? First, the loss at the entry to 5. The first loss is entry to 5. I will write on this is the first loss plus second loss is the friction loss, that is major loss, that is HF1 you can say, plus third loss is due to the sudden expansion of the pipe. Loss due to sudden expansion, sudden expansion. This one is the third number. And then again the second pipe flow, that is friction, that is HF2, plus at the exit there is exit loss. So loss due to exit from pipe. So these five losses we will see from this figure. One is due to this entry loss to the pipe, and then loss due to expansion and loss due to exit, and then frictional resistance of the flow due to viscosity of the liquid, that will be the frictional factor, and then the head loss due to the friction you can consider into the pipe 1 and pipe 2. Okay, so we have to find out the this friction factor here. Now you know the formula for each losses. So one by one we will take and we will try to solve it. And so from the table number one, I will write down from table number one. Using table number one, we have seen in the last class. So that table number one, the different losses are given here. Loss due to sudden expansion, loss due to entry to the pipe and exit to pipe. We require this only in our case. Okay. So first loss due to first is the loss due to entry to pipe, and from table number it is given by 0.5 V square upon 2G. You can see here it is given entry to the pipe. This okay, the value is 0.5 V square root 0.5 into V square upon 2G. So I will write down here. So loss equal to 0.5 V square upon 2G. So here velocity in pipe 1 is V1 at the entry, so V1 square upon 2G. Okay. Then again, you can write down second equation. Loss of head in a pipe due to friction, and you know that the SHF1 is equal to FL1 V1 square upon 2G into D1. Okay, so this frictional loss, you know, it is not given in minor losses table. Now, third loss is loss due to sudden expansion. Loss due to sudden expansion, and that derivation already we have done in lecture number 39. So if you write down this, it's nothing but here sudden expansion, this one. Okay, the value is P1 minus V2 E square upon 2G. So I will write down here once again this one, V1 minus V2 whole bracket square upon 2G. This is loss due to sudden expansion. Then HF2, again the friction loss in pipe number 2, loss of head due to friction in pipe 2. In pipe 2, that is HF is equal to F L2 V2 square upon 2G into D2. Okay, this is the friction loss in pipe 2. And then the last one is the exit from the pipe. Only these 5 losses will be there as per your figure. So exit from pipe 2. So here you can write down it is V2 square upon 2G. So this is the minor losses and losses in the pipe flow network. Now we have to find out the friction factor. So I will write down all the terms. First is zero point 0.5 V1 square upon 2G. I will write down first 0.5 V1 square upon 2G plus the loss due to friction HF1, that is here FL1 V square upon 2GD1. So I will write down F is the friction factor. What we have to find out, this value we don't know. So this we have to find out here. FL V1 square upon 2G into D1. Okay. Now what is the third loss? In this case, what is the third loss? So the third loss will be this loss of head due to sudden expansion, and that we know it is V1 minus V2 whole bracket square upon 2G. Okay. Then 4 loss is again the friction loss in pipe number 2. So L1 here, so it will be L2 here, and V2 square upon 2G into D2 into D2. And then again the last your friction loss, as I said, is loss due to exit from the pipe 2, and that is nothing but V2 square upon 2. V2 square upon 2G, and that is equal to 5 meters. That is the total differability in the reservoir level 1 and 2. That is the 5 meter. So I write on this. It is solved the now putting all these values and take the 2G right side. So I will take 2G right side. So what will be the equation? 0.5. You know the V1? We don't know the V1. So before going to that, I will say that this is the equation number 1. I will say this is the equation number 1. And then we know that from the continuity equation, okay, A1 is equal to V1. So Q is equal to A1 V1 is equal to A2 V2 from continuity equation. Continuity equation. We know that the discharge is same from the 5 in series. This is the continuity equation. So if I will write down, so V1 is equal to Q times A1, and Q we know that the discharge is already given in 50 LPS. So 50 LPS into 50 into 10 raised to minus 3 meter cube per second. So it is meter cube per second. Okay. Divided by area pi by 4. Diameter of pipe 1 is 0.2 whole square, that is meter square. So we will get the velocity V1, that is 1.59 meter per second. Similarly, from the continued equation, you can find out the velocity v2 q upon a2. Okay, so discharge will be same. There is no change. Pipe in series. Then pi by 4. Diameter of pipe 2 is 0.3 square. So it will be when you solve 0.707 meter per second. So velocity v1, v2 we know. Now this value of velocity put in the putting
Yaar,
given value putting given value given uh, and find that value. Okay, putting given value and calculated values in equation number 1. Equation 1 we have prepared due to the minor and major losses, but here f we don't know. Here this f we don't know. Okay? So that f we will put as it is. So if you write out, so 0.5 2 GB are taken right side. So v1 square means 1.59 square plus f will be the this friction factor. You have to find out. यही हमको मालूम करना है ना। और दूसरा एनर्जी ग्रेडियंट लाइन ड्रॉ करने के लिए बोला था, वो ऑलरेडी हम लोग ने ड्रॉ कर लिया है ना। तो यहाँ पर अब L1 is 300 meter into V1 square 1.59 square upon D1 is 0.2. 2 GB are taken right side. Then loss due to expansion you can find out by putting the value 1.59 minus 0.707 whole square divided by 2g will be taken. That's why there is no division. Okay, so no need of writing division here because 2g we are taken right side plus f into L2 is 200 meter, velocity 2 0.0707 whole square divided by pipe diameter 2, that is 0.3, plus V2 square, V2 is 0.707 whole square, and all this term is equal to 2 into G into 5. Okay. Now solve this. After solving this, you get this friction factor term is in two equations. We will put this both at one side and all the values will take the another side, and G is nothing but 9.81 meter per second square. You know this. So the value of G you should put there. So after finding out, this friction factor will be F is equal to 95.51 upon the value of left hand side 4125. So if you find out this, then friction factor will become 0.023. So this you have to find out friction factor in this example. Okay, so maybe sometimes they will ask the length of pipe 1, maybe diameter of pipe 1, okay, or the friction factor is given. So maybe they will ask. So likewise, you have to solve the example by using the uh, Bernoulli's theorem between the two reservoir R1 and R2, and by putting the total equation of the losses due to minor and major losses, and then the difference, total difference if it is given, then that put that value you can find out the whatever they will ask. Okay. So this is nothing but the example yesterday I have given to homework. So I have solved here. Today is your lecture number 41 is running. Now we will see that concept of the pipe in the series and the parallel. Okay. So if you know that pipe in series or pipe in the parallel, pipe in a parallel means if you can see. So I will write down the second half of this lecture. Pipe pipes in series and pipes in parallel. Pipes in parallel. Okay. So first we will see the pipe in series. Already we have solved this example previously. That is the pipe in series. Okay. So if I draw the pipe in series, this is the reservoir one. Okay. From reservoir one to reservoir two, the pipe is flowing in the series. The liquid is flowing in a series. So this one, pipe one. Then there is sudden expansion, pipe two of length. Then there is maybe sudden contraction or expansion, pipe three, and then your reservoir two, reservoir reservoir two. Liquid is flowing from here to here. Here some level and some level here. Okay. So this pipe one discharge from pipe one Q1, discharge from pipe two is Q2, discharge from pipe three is Q3, having a length L1, so pipe two length L2, and pipe three length L3. Okay, this is the reservoir. I will write on R1, and this is the reservoir R2. Okay, and this is the your head in the reservoir number one. Okay, this one is the total head loss, you can say. Okay, and that is nothing but H is equal to HF1 plus HF2 plus HF3. Okay, and discharge in this case when the pipe is series. So this is nothing but pipe in series we are studying. Pipe in series. Okay, because all the pipe are placed in the series and so here this L1, L2, L3 and the diameter of the pipe here T1, T2, T3. It loss due to friction Hf1, F2, F3. Okay, so this is nothing but your pipe in series figure. So two or more pipes can be connected in series as in figure number, I write on the figure number 5, pipe in series, pipes in series. So two or more pipes can be connected in series so that said discharge is passing through them, but each one will be have friction aid as per its own length, diameter and friction factor. So HF1, HF2, HF3, this will be different, discharge is also different. Discharge will be same because here in pipe in series the Q is equal to Q1 equal to Q2 equal to Q3 plus so on. Okay, plus so on. So here some number is 7. Similarly, this one is the pipe in series, and here HF is equal to HF1 plus HF2 plus HF3 plus dash dash dash. The losses are different. Okay, okay. So it is again the equation given. Okay. So this is nothing but when the pipe in series, then Q is equal to Q1, Q2, Q3. Okay. Now if you see the pipe in the pipe in the parallel, pipes in the parallel, pipes in the parallel system. So if one pipe there is pipe flowing and then suddenly there is two pipes from the discharge is okay, it will be divided into two pipe. So you can say that this is nothing but the pipe in the parallel. So this pipe in the parallel, this is here Q. Now here discharge is divided. Okay, so it may be Q1 and it may be Q2. Okay, or in case of reservoir system also you can show. And then again this is number here Q. Here if I will draw the figure another way, this one pipe having a diameter some front with another pipe having diameter something different. Okay, and this is your reservoir one R1. Okay, and then pipe in a parallel, and this is reservoir two. Pipes are connected in the parallel. Okay. So here this is the total head loss. Here this is nothing but H F is equal to HF1 is equal to HF2 and so on. Here the discharge in pipe 1 and pipe 2 it may be Q1 or Q2. Okay, this is the pipe 1 and pipe 2. So here HF is equal to HF1 is equal to HF2 because friction factor is different and length or it may be same, it may be different. So this figure number 6 is pipes in parallel. Pipes in parallel. When the pipes are parallel, then your discharge Q is equal to Q1 plus Q2. Two different pipes, they are parallel, so their discharge will be different. They are not same. Okay, Q1 plus Q2 plus Q3. How many pipes you are putting into that? So Q3 and so on. Here two pipes you are putting, so Q1. Here only two pipes are there, so you can write down Q is equal to Q1 plus Q2. If three pipe is there, then Q1 plus Q2 plus Q3. If four pipe is there, Q1 plus Q2 plus Q3 plus Q4. Two pipes in there, that's why I will written Q1 plus Q2. So in parallel system, your HF will be the loss due to friction will be same in all the pipe system. Test. Okay. So these are the pipes are in parallel or in series. You have to write down like this. Okay. So these are nothing but the concept of pipes in the parallel and the pipes in the series. If you solve the problem, then you can easily understand uh, problem. Problem in series already we have solved. Example number one, that problem is the series problem. But still we are going to solve the problems of the pipes in the parallel. So we will have very less time, 10 minutes, which is 10 to 15 minutes there. cover it up. So we go to the problem. Okay. So I will write down example number 2. Example of pipe in pair. Example pipes in pair. Parallel system. Okay. So write on example number 2. Two pipes, two pipes of length 2,500 meter each and diameter and diameters 80 centimeter and 60 centimeter respectively are are connected connected in parallel. Coefficient of coefficient of friction, it is given 0.006. The total flow is equal to 250 liter per second. Find rate of flow in each pipe. So we have to find out the rate of flow in each pipe. It means that what we have to find out? You have to find out the Q1 and Q2 you have to find out. If I will write down the solution, so here it is given that L1 is equal to L2 is equal to 2,500 meter. Okay, and Q is equal to Q1 plus Q2. Why Q1 plus Q2? Because this pipe in a parallel. Just now above yourself. So two pipes are there. That's why only Q1 and plus Q2. Three pipe अगर होता तो तीन pipe होता तो Q1 plus Q2 plus Q3 हम लोग लेते. And that is given 250 liter per second. If you write in the meter cube, so 2.5 0.25 meter cube per second. I will write on a meter cube. It will be liter will be converted. It is divided by 100. Okay. Now pipe is in parallel means HF is equal to HF1 is equal to HF2. So HF1, if I will write on 4 times F dash LV square upon 2G into D. So you can add on 4 L1 V1 D1 write down. इसी तरह HF2 if you write down 4 F1 F dash L2 V2 square upon 2G into D2. Okay. So this. So you know that the friction factor it is denoted by F and it is equal to 4 times of F dash, and this F dash is nothing but coefficient of friction what is given in the example. Example coefficient of friction given. So you know that F is nothing but 4 times of F dash, and F dash is the coefficient of friction. F is the friction factor. Okay, so you know this, so you can write down this formula. This is nothing but your formula. Actual we are writing the HF is equal to f into lv square upon 2 gt. Okay, but since f is equal to 4f dash, so here I have written the 4f dash. Okay, now we know that in pipe in parallel hf1 is equal to hf2. If I write on 4f1 L1 V1 square upon 2G1 will be equal to 4 F dash L2 V2 square upon 2G into D2. Here L1 is equal to L2, that is 2500. So you can write down L. Okay. So here this term, if I will say that these terms will be cancelled. Okay. This term L is also same, will be cancelled. 2G, that is also cancelled. What will be remain? What will be the remaining terms? Remaining terms be V1 square upon D1 is equal to V2 square upon D2. This will be remain. I will say this equation number 1. So what will be the V1 square? V1 square is equal to D1 upon D2 V2 square. Now D1 we know 80 centimeter, that is 0.8 meter. D2 we know 60 centimeter, that is 0.6 meter. Putting this value V1 square is equal to zero point 0.6 upon 0.8 upon 0.6, sorry, V2 square. So if you write down, it will be V1 square is equal to 1.33 V2 square. If I write down V1 is equal to under root of 1.33 V2. So V1, if you write down, it will be root 1.155 V2. So this will be the relation between the velocity 1 and velocity 2 due to the pipe diameter difference. Okay, so I will write down this equation number 2. Equation number 2. Now we know that Q is equal to Q1 plus Q2 in case of pipe in parallel. We know the value of Q, we don't know the value of Q1 and Q2, we don't know. Okay, so I will write down 0.25 meter cube is equal to 5 by 4 D1 square into V1, okay, plus 5 by 4 into D2 square into V2. Now we know that V1 is equal to, from equation number 2, I will write down here from equation number 2, from equation 2, put V1 is equal to 1.155 V2. Okay, so I'll put the value here. So I will write down 0.25, and 5 by 4 is common, it will come here, it will be 4 by 5 is equal to D1 is 0.8 square into V1 is 1.155 times V2. All term will become in terms of V2 plus D2 is 0.6 square into V2. Okay. So if you find out, the V2 will be equal to 0.318 upon 1.099, and it is equal to, 0.289, or you can approximately 0.29 meter per second. Now V1 you can calculate from equation number 2, that is 1.155 times of V2, 0.29. So V1 will be 0.33 meter per second. Now the velocity 1 or 2 we know, an area of pipe we know, as we know the diameter. So Q1 you can find out, Q1 is equal to pi by 4 into V1 square into V1. So we'll put the value pi by 4 into V1 is 0.8 whole square into V1, just you find out 0.33. Putting all these values after calculation, the discharge Q1 you can find out, and it will be 0.167 meter cube per second, or you can write down 167 liter per second. Multiplying it 1000. Similarly, you can find out Q2, that is pi by 4, 0.6 V2 square into V2 is 0.29. So you can find out this V2 value, and it is coming 0.0819 meter cube per second. So you can write down this is 0.082, or you can write down 82 liter per second after multiplying, converting to the liter per second. So Q is equal to Q1 plus Q2, you know. So Q1 is 167, Q2 is 82. If you add, it will coming as 249 liter per second, and it is approximately equal to, 250 liter per second. That is given in that one. So this is when the pipe in the parallel, you have to solve the example like this, and very simple examples are there. One, two example more, we change the values, diameter or length of the pipe, then we can solve different types of example based on this. So this is what about your today's lecture. So you have another class. We will stop here. Thank you for joining. Tomorrow also first lecture. Please join on time. Okay. And if you have any question, you can ask with me, or otherwise. So I will requesting students they should join on time, so that there should not be any delay. Okay. If you have any question, you can ask with me. Otherwise,